7 hours ago, the European Space Agency released what they call the closest ever photo of 3I Atlas, the interstellar object that has both amazed and terrified the world, billions of dollars in space technology. 7 Mars orbiters positioned for the once-in-a-lifetime photo. And what did we finally get? A faint white dot that looks like AI sneezing on the lens. Within minutes, social media exploded. Not with admiration, but with outrage. Amateur astronomers with backyard telescopes captured sharper images of comets millions of kilometers away. Yet the U.S. Space Agency, with the Mars rover equipped with the most powerful camera ever sent to another planet, remained completely silent. Excuses about government shutdowns became meaningless, especially when you realize that Chinese orbiters and the United Arab Emirates spacecraft are also mysteriously silent. After hearing this, Atlas will disappear in less than a week behind the Sun, obscured from all Earth-based telescopes, just at the moment it should be most active. And if Harvard physicist Avi Loeb is right, what happens next could change everything we thought we knew about what might exist in our cosmic neighborhood. If you're as fascinated by this mystery as I am, please hit like and subscribe to the channel to get real-time updates on this story. Let me know in the comments where you're listening from, what time it is, and whether you think we're being told the whole truth about 3I Atlas. And if you want to help our community grow, please share this video on social media, X, Facebook, Reddit, or your favorite messaging apps. Thanks for your continued support. Chapter 1. A photo that shook the internet. The 7th and 8th of October 2025 will be remembered as the moment the space community collectively lost patience. For months, we had waited for this moment. 3I Atlas, the confirmed interstellar object, the third ever discovered passing through our solar system, was making its closest approach to Mars. 7 different spacecraft from 4 space agencies were positioned to capture unprecedented images. All expectations were real. Scientists promised us clarity, answers, even evidence of the true nature of this object. Then the images were released. The ExoMars Trace Gas Orbiter from the European Space Agency, positioned just 30,000 kilometers from 3I Atlas at its closest approach, on the 3rd of October released a series of images that can only be described as utterly disappointing. A faint white dot moving slowly against the Martian backdrop. No details, no structure, nothing to help us understand whether we were looking at a natural comet or something far stranger. The backlash was immediate and fierce. Astronomy Vibes, a popular space commentary account. On social media, X posted a side-by-side comparison photo that went viral within hours. On one side, a sharp, detailed image of Comet Lemon, taken by an amateur astronomer with a simple, mirrorless camera. On the other, the image of 3I Atlas released by the European Space Agency. The caption read, "If a simple, mirrorless camera can capture Comet Lemon at Mars. NASA cannot photograph 3I Atlas when it flies near Mars." The post currently has over 40,000 retweets and is still growing. But it was the next post that truly hit a nerve, billions of dollars in funding. And this is the best photo they have. It looks like a weather balloon in a foggy field. To understand why people were so angry at Mars, you need to understand what we expected versus what we got. The Casio camera on the ExoMars Trace Gas Orbiter has an angular resolution of 11.36 microradians per pixel at a distance of 30,000 kilometers, which corresponds to 40 kilometer pixel on 3I Atlas. To put it simply, the estimated nucleus of 3I Atlas is about 54.6 kilometers wide, meaning the entire solid core of this object at best only occupies a small part of a single pixel in these images. But here's the interesting part: the European Space Agency knew this beforehand. They knew their camera was designed to image the bright surface of Mars from a few hundred kilometers away. not faint objects tens of millions of kilometers distant. Nick Thomas, the principal investigator of the camera, admitted this in an official statement. This was a very challenging observation for the equipment. Comets are more typical targets by 10,000 to 100,000 times. So why did Mars release images they knew were insufficient? Why build up expectations for months only to deliver something that provides no new information? The official story is they have released what they have, that these are the best possible images from the available equipment, but at this time it seems deliberately almost like a pressure release valve. Give people something, anything to look at, while the real data is kept secret. Because, make no mistake, there are much better images, much better. And they are being withheld. Chapter 2. The Missing Gem. While the European Space Agency released speckled images of the Mars rover, the U.S. Space Agency captured something completely different. The HIRA camera, short for high-resolution imaging, science experiment, is the most powerful camera ever sent to another planet. Its resolution is so precise that from Mars' orbit it can distinguish objects the size of a dining table on the red planet's surface. When BAI Atlas made its closest approach to Mars on 310, the HIRA camera has a resolution of about BA 0 km per pixel at the object's distance. This figure is 10 times better than what the European Space Agency's camera achieved. If there is any structure, any unusual feature, anything inconsistent with the natural comet-Mars hypothesis, then HIRA certainly would have seen it. Avilo, a physicist at Harvard University who has been tracking Atlas since its discovery, said bluntly in his latest blog post, "The brightest pixel in HIRA's image will provide the best ever limit on the size of Bay Atlas. We all hope the HIRA team will release their images as soon as possible." This was written on 7/10. Now it is 8/10. Still nothing. The official explanation is the U.S. government shutdown. Over 15,000 employees of the U.S. Space Agency. More than 80% of the agency's workforce have been furloughed. The agency's website is not updated. Public information has stopped. This is bureaucratic paralysis at the worst possible time. But this is illogical. The European Space Agency has released their images. They are a European agency completely unaffected by U.S. political turmoil. China's Tianwen-1 orbiter is also positioned to observe Bay, Alaska, with its moderately high-resolution camera. Also silent, the Hope orbiter of the United Arab Emirates, equipped with the Emirates Exploration Imager, also has a clear view. Not much space agencies, many governments with bureaucracies and completely separate priorities all at once cannot or will not release their best data on the most scientifically significant object to visit our solar system. In many years, this pattern is hard to ignore. Social media exploded with speculation. Some said it was coordination. Others said something had been seen. Needing careful consideration before release, conspiracy theorists suggested the images showed something so unusual that releasing them without proper context would cause mass panic. The final theory sounds absurd, until you recall what happened last week with amateur observations, because while professional space agencies keep their data secret, amateur astronomers captured images that raise more questions than answers. Chapter BA, when amateurs see what experts don't want to release. 310. Exactly the day BAI Atlas made its closest approach to Mars, a Portuguese amateur astronomer with the username Dobsonian Power uploaded an image that instantly went viral using only a backyard solar telescope and some powerful digital enhancement techniques. He captured what appeared to be an angular structure inside Bay Atlas' dark geometric shapes. Protrusions that don't match the typical diffuse light of a cometary. Mars. He added a very simple but suggestive caption. What the hell is that? Within 6 hours, the image was shared on every major astronomy forum, Reddit subforums, and social media platforms. Immediate reactions split into two camps. One group saw clear evidence of artificial structures, evidence that Beiji Atlas is not what mainstream science claims. The other group dismissed it as pareidolia. a classic pattern. The human tendency to see patterns where none exist, amplified by processing errors from unsuitable equipment. The skeptics had solid technical arguments. Solar telescopes use specialized filters designed to observe the sun's extreme brightness, not faint deep space objects moving at interplanetary speeds. Simple devices are not made for this type of observation. Plus, powerful digital enhancement techniques to compensate for insufficient setup. And basically, you are asking an algorithm to generate details that do not really exist. It is like in astronomy when you zoom in on a blurry photo, until you start seeing faces in the noise. But this is when the story becomes complicated. Dobsonian Power is not a conspiracy theorist, randomly on the internet with a cheap telescope and too much imagination. He is a respectable amateur astronomer who has shared legitimate astrophotography work for over a decade. His YouTube channel has careful documentation of equipment, methods, and image processing procedures. This is not someone trying to fabricate evidence for views, and when asked about unusual structures in the BA, Atlas images, he does not repeat crazy claims. Instead, he acknowledges uncertainty and promises to try again. When the object becomes visible from Earth in early November after passing behind the Sun, his reaction is very scientific and appropriately cautious. This makes the reaction to his images even more remarkable within 2 to 4 hours. Many websites published special articles to debunk his photos. The amateur astronomer captured strange BAI Atlas images. Here is why. It is not what it seems. This moment appears coordinated. The tone seems defensive, as if AI needed to quickly establish a story that nothing unusual was captured, that any apparent anomaly was just a technical error before the image could gain too much traction. And then the image enhancement battle began. Users across Reddit, Twitter, and various conspiracy forums started downloading the original images from the European Space Agency and running them through their own processing algorithms. Some used standard astronomical image stacking techniques. Others used AI image enhancement tools, designed to enhance low-resolution photos. A few players went all out with machine learning models, trained to recreate fine details from limited data, wildly varying results. Some showed nothing more than slightly sharper versions of the same blurry spot. Others revealed what appeared to be distinct geometric patterns, edges, structures that seemed too regular to be natural ice and rock. The problem is when you start processing an image aggressively, especially with AI tools, you are no longer looking at what is really there. You are looking at what an algorithm thinks should be there, based on its training data. If you train an AI on thousands of spacecraft images and then ask it to enhance a blurry spot, it will likely generate spacecraft-like details because that is what it has learned to recognize. It is a scientific dead end wrapped in the illusion of clarity. But the viral spread of these enhanced images has had an unintended effect. They have made the information stream so murky that distinguishing between legitimate amateur observations and outright fabrications has become almost impossible. Within 4 to 8 hours after the European Space Agency image was released, there were dozens of versions said to have been enhanced circulating online. Some showed metallic surfaces. Others depicted what looked like solar panels or antennas. A few even included visible running lights and thrusters, most clearly digital artwork fakes, created by people with too much time and Photoshop skills that are too good. But mixed in that chaos were a few images that felt different, more subtle, less sensational. Images that showed just enough unusual regularity to make you wonder if something real was being hidden, obscured by the obvious wave of deception. Chapter 4. Leaked Information Hard to Suppress on Forum, or page 411. Anonymous Users. On the Supernatural forum of page 4, posted what they claimed was insider information about BAI Atlas. The post was simply titled Leak. European Space Agency data, and began with a statement of identity specific enough to sound legitimate, but vague enough to maintain anonymity. I am a PhD researcher working with the European Space Agency with continuous access to combined observational data of BA. Atlas. Leaks on the internet happen all the time, mostly easily dismissed as creative fiction or blatant provocation. But this case is different. The technical details are very concerning. The poster does not make crazy claims about alien invasions or secret military operations. Instead, they present a series of specific observed anomalies that, if true, would fundamentally challenge our understanding of the nature of BAL Atlas. The first anomaly is chemical impossibility. According to the post, spectral analysis shows BAL Atlas is releasing about 100 kilojoules of nickel gas per second, but almost no iron gas is emitted. In normal star and planet chemistry, nickel and iron are inseparable twins. They form together in supernova explosions, travel together through interstellar space and appear together in comets and asteroids. Finding abundant nickel with almost no iron is like finding smoke without fire. It violates basic assumptions about how matter behaves in the natural space environment. The second anomaly is thermal contradiction. The object is releasing a large amount of gas and dust, a characteristic sign of an active comet being heated by the sun, but infrared observations show it remains cold. Much colder than it should be based on the outgassing rate and proximity to solar radiation. The comparison is like seeing an AI sweating profusely in a freezer. The physics do not match the observation. The third anomaly is the precise orbit. The post mentions what Avi has publicly said, that BAL Atlas has an orbital inclination of only 4.89 degrees relative to Earth's ecliptic plane. But the poster on 4chan added something that Lowe did not emphasize. The orbit is not only unusual, it is a perfect straight line from the direction of the galactic core with no wobble, no deviation, no sign of interference. Gravitational disturbance from nearby stars over millions or billions of years. It moves through interstellar space as if it has been targeted. Then comes the part that elevates this post from an interesting speculation to something darker. The poster claims the object fits the profile of what they call a post-biological entity. Not a natural comet, not a conventional spacecraft, but something in between. They describe it as having a BA phase particle engine with an estimated power of 7.5 megawatts continuously transmitting an active signal, and according to them it is probing our solar system. The post concludes with a theoretical framework, proposing that by Atlas could be a macroscopic quantum object, specifically something called a cuban, a strange theoretical structure from particle physics, a type of soliton non-topological Zika that can exist on scales much larger than subatomic particles if stable. A cuban could have properties that seem impossible according to normal physics. It could be extremely dense while appearing diffuse. It could absorb and redistribute energy instantly across its entire structure, explaining the thermal contradictions. It might even explain the nickel without iron problem. If the intrinsic quantum state of carbon favors producing certain isotopes within 18 hours. The post was screenshotted and shared on Reddit, Twitter, and dedicated unidentified flying object research forums. The topic on the conspiracy theory subreddit discussed it, accumulating over 2,000 comments before moderators locked it for violating rules against unverified claims. But locking the thread did not stop the conversation. It just moved to other platforms, fragmenting into about 10 parallel discussions each, pulling the original post in different directions. Some focusing on chemical anomalies, others focusing on the Cuban hypothesis. A few began linking it to previous claims that by Atlas could be the source of the WOW signal from 1977, Chapter 5. Question 5,400 kilometers. NASA's Perseverance rover in the J0 crater on Mars's surface captured something in the night sky. Images from its right navigation camera show a long stretched light trail about 4 times longer than its width. At first glance, it looks like a long exposure photo, typical of a moving object. Comets and asteroids often appear blurred in images when the camera tracks stars instead of the object itself. Normal, except the math does not work out that way. When people started calculating the apparent size of the light trail, based on Perseverance's known camera specifications and the distance to Bi-Atlas at that time, they arrived at a worrying figure of 5,000 kilometers long. That is not the nucleus of a comet. It is not even a comet with a tail. That is something completely different to compare with the Earth's diameter of less than 13,000 kilometers, if this represents the actual physical size of Bi-Atlas. We are looking at an object nearly 4 times wider than our entire planet. Social media exploded with speculation. Could Bi-Atlas actually be a giant cylindrical ship that has long concealed its true size and shape behind a diffuse cloud of gas and dust? This moment is significant. The image appeared just 1 day after flying past Mars, at a time when all professional space agencies were mysteriously silent. Some saw it as confirmation that something profoundly unusual had been photographed, something not easily explained. Speculation reached such a high level that Congresswoman Anapolina Luna, a member of Congress known for her interest in unexplained aerial phenomena, directly contacted Aviel for his analysis. Think about that for a moment. A sitting member of the U.S. House of Representatives felt compelled to contact a physicist from Harvard about a photo from Mars that is not a normal procedure. It shows that AI in official channels was concerned enough to want an expert explanation outside the usual communication lines of the U.S. Space Agency. The reaction of Lowe was very thorough and on the surface reassuring. He calculated that the navigation camera of Perseverance has an angular resolution of 0.33 milliarcseconds per pixel at the distance of Bi-Atlas. When the image was taken about 8,000 kilometers from BA, that corresponds to about 12,500 kilometers per pixel in the image spanning about 4 pixels, giving you a length of about 50,000 kilometers. But Lowe argued that this is a byproduct of composite imaging. The streak does not show the actual size of Bi-Atlas, it shows the path the object took across the Martian sky. During a long integration time, possibly about 10 minutes of stacked exposure, his reasoning is very solid. Mars orbits the Sun at a speed of 24 kilometers per second. Bi-Atlas is moving at 6.7 km per second relative to the Sun in the opposite direction, giving it a relative velocity of over 90 kilometers per second compared to Mars. In those 10 minutes, that is exactly 4,000 kilometers traveled. Perfectly. Matching the length of the observed streak. The shape is not the object, but the motion of the object blurred over time. The issue is resolved. Right, the cylinder theory was rejected by basic physics and careful mathematics, except Lowe inserted a sentence into his analysis that conspiracy theorists cling to like a lifeline not writing, if the images from the navigation camera represent single snapshots. With exposure times under 3.228 seconds, then the brightness and angular length of the observed source imply that it is not Bi-Atlas. In that case, the source could be much closer to the camera, possibly blurred into an elongated image with smaller spatial size and lower speed weight. If these are single frames, then what Perseverance captured is not Bi-Atlas at all, it is something else. Something closer to Mars. That phrase opened a door that no explanation since then could fully close. Because NASA has not confirmed whether the image is a composite or a single frame, they have not released metadata. They have not provided exposure time or number of stacked images. The government shutdown reason also applies here. No staff to process requests. No AI to verify basic technical details about how the image was taken. Chapter 648. Years silent. 15/8/1977. The Big Ear Radio Telescope of Ohio State University detected an unusual 7.2-second radio energy burst so remarkable that astronomer Jorian circled it on the printout and wrote the word "wow" in red pen. Nearly 50 years later, that signal remains one of the greatest mysteries in the search for extraterrestrial intelligence. It came from the direction of the Sagittarius constellation. Near the densest star fields of the constellation, it is a narrow-band signal focused at a specific frequency, and it has never repeated despite hundreds of follow-up observations. Thousands of hours listening towards the same patch of sky, nothing but that one burst 48 years ago, and then eternal silence until Avili calculated the numbers about by Atlas. He calculated the position of the object on 12/8/1977, just 3 days before the WOW signal was detected. The answer, about 600 astronomical units from Earth, about 600 times the distance between Earth and the Sun. But more importantly, he calculated the direction that BAI Atlas was heading at that time. Right ascension, 19 hours. 4 minutes declination, 19 degrees the WOW. Signal came from right ascension, 19 hours 2 minutes. Declination, 27.2 degrees. These directions are about 9 degrees apart in the vastness of space, with random objects coming from all directions. The probability of this arrangement is about 0.6%. Not impossible, but very suspicious. Lee did not stop there. He asked the next reasonable question if BAI Atlas sent the WOW signal. From a distance of 600 astronomical units. How powerful must the transmitter be? The calculation is very simple. The detected intensity is from 14 to 2. 1.2 Jansky over a 10 kilowatt bandwidth at a distance of 600 astronomical units. That corresponds to a transmitter output power from half a gigawatt to 2 gigawatts. For reference, a typical nuclear reactor on Earth produces about 1 gigawatt. So we are talking about the energy level of a nuclear power plant, focused into a narrow radio beam, which is not impossible for an advanced civilization. In fact, it is quite reasonable if you are trying to send a signal. Detectable over distances of light years without wasting energy broadcasting omnidirectionally. There is another detail that makes the alignment harder to dismiss the WOW signal. Was observed at a frequency of 1/420/04556 MHz. Blue shifted by about 10 km towards Earth compared to the hydrogen line. That blue shift indicates the source is moving towards us. BA Atlas is currently approaching the Sun at a speed of about 60 km/s. Lee suggests that if this object is capable of maneuver, it may have moved slower in 1977 and then accelerated after detecting potentially habitable planets in our solar system. A precise pulse, a single scan, has checked for signs of a technological civilization before proceeding with a closer approach. This is what makes the whole connection frustrating. It is very easy to point a radio telescope at BA Atlas listening at the hydrogen line frequency. If it is transmitting, we will know within a few hours. If it is silent, the connection to the WOW signal is probably just a coincidence. A simple test. A definitive answer. Yet, as Lee noted in his most recent blog post, no radio telescope has reported data on BA Atlas. The Arecibo telescope was destroyed. The Green Bank telescope has not released observations, not even SETI. Organizations specialized in searching for extraterrestrial signals have publicly announced any monitoring efforts. The silence from the radio astronomy community is deafening. 7 orbit should not exist. Orbit. Imagine you throw a dart and a globe from the other side of the room while blindfolded. Now, imagine that dart not only hits the globe, but also lands within a few degrees of the equator. That is the statistical impossibility we are dealing with when looking at how BA Atlas entered our solar system. Interstellar objects can come from any direction. They should be randomly distributed across the celestial sphere, coming from all possible angles. However, BA Atlas arrived with an orbital inclination of only 4.89 degrees relative to Earth's ecliptic plane, less than 5 degrees. That places it within less than 1% of possible arrival angles. Lee has emphasized this point in every interview, every blog post, every public statement since July. The orbit is unusual. Not only unusual, but statistically impossible for a random interstellar object. To understand why, you need to think about how objects move in the galaxy. Stars in the galactic disk orbit the galactic center at an average velocity. But they also have random motions, up, down, and sideways like bees buzzing around a hive. That randomness means objects ejected from other star systems will arrive at our solar system from all directions with nearly equal probability. No preferred direction. There is no cosmic highway funneling interstellar visitors into our ecliptic plane. And before AI suggests that, perhaps objects from the galactic disk naturally arrive at shallow angles. That has been addressed. The galactic disk itself is tilted about 6 degrees relative to the ecliptic plane of the solar system. We are in 6 degrees is 10 times larger than the inclination of BA Atlas. If this object came from a typical star system in the galactic disk and was ejected randomly, we would expect it to arrive at a steep angle, not a shallow one. This arrangement is the opposite of what galactic geometry would predict. Compare BA Atlas with the only 2 other interstellar objects we have detected. Oumuamua, discovered in 2017, arrived with an inclination of 122 degrees, a crazy tilt coming from above the solar system plane. Borisov, discovered in 2019, had an inclination of 44 degrees, still steep, consistent with random arrival from interstellar space. Both objects behaved exactly as expected for natural interstellar visitors. Alas is the exception, the abnormality, the thing that does not fit the rule. The probability calculation of this arrangement assumes random directions with less than 1% chance. Some colleagues objected, suggesting that perhaps his statistics were too conservative. Maybe the actual probability is closer to 5 or 10% when you take into account selection effects and various observational biases. All right, even at 10%, you're still looking at something that should only happen once in every 10 interstellar objects we detect. And we have only just detected BA. The BAth object is a rare exception rather than the rule, not supporting coincidence. Now layer that on top of everything else. The WOW signal arrangement also has less than 1% probability. Chemical anomalies with nickel but no iron. Thermal shield colors. High-resolution images. Missing from many space agencies. The government shutdown happened right when we needed the U.S. Space Agency the most. Any of these could be explained. Coincidence, measurement error, bureaucratic incompetence. But when you start stacking anomalies, when you start multiplying small probabilities together, the composite impossibility becomes harder to refute. There is a principle in statistics called the prosecutor's fallacy, which is the error of treating many independent low-probability events as if they are related when they are really just random coincidences happening together. If you flip a coin enough times, eventually you will get 10 heads in a row. That does not mean the coin was rigged. It just means you flipped enough times for unlikely sequences to occur. Skeptics will argue that is what we are seeing with Bi-Atlas, a natural interstellar comet coincidentally having some unusual but ultimately explainable characteristics, coincidentally appearing together in the same object. Unlikely, yes, but not impossible. Counter-arguments also hold value. If something walks like a duck, quacks like a duck, swims like a duck, and has duck DNA, at some point you have to consider the possibility it really is a duck. Or in this case, if an object arrives on a statistically unlikely orbit showing chemical signs, not matching natural processes, correlating with an unexplained radio signal lasting 4.8 years, and causing many governments to withhold their best image data. It may be worth seriously considering that we are not looking at a random chunk of ice and rock from another star system. Chapter 8. When the question becomes dangerous. A strange thing started happening around 5:10. Users on multiple platforms began reporting their posts about BAY Atlas had disappeared. Not flagged or marked as misinformation, but actually vanished. A Reddit user documented posting a detailed thread analyzing chemical anomalies from a leak believed to be from the European Space Agency. The thread attracted cumulative attention with hundreds of upvotes and dozens of comments. Within 2 hours, it disappeared. Not deleted with a moderator explanation, but simply wiped out. When users tried to repost, the posts were not approved, silently banned without notification or explanation. On Twitter, now X social media, some accounts noticed similar patterns. Astronomy Vibes account that went viral for criticizing European Space Agency images reported a significant drop in engagement. After 710 posts that would normally reach tens of thousands suddenly stalled at a few hundred views with no official restrictions. No warning messages, just algorithmic suppression, quiet enough to deny but strong enough to be effective. Other content creators in the space astronomy community also noticed the same. Videos about bi-Atlas that would normally perform well only received a fraction of their usual reach. YouTube raised another issue. Content creators posting videos analyzing speculation about bi-Atlas began receiving demonetization notices for various reasons. Some flagged for discussing sensitive topics without proper context. Others classified as potentially misleading scientific content. A few labeled with blurred warnings, but clearly marked as content. Possibly unsuitable for all advertisers. A very clear pattern. You can make a video saying bi-Atlas is definitely just an interstellar comet. And mainstream science discovered it. That's fine. Monetized. Promoted. But if you suggest there might be anomalies worth investigating, suddenly your video becomes advertiser unfriendly. Facebook's approach is the most public. The platform's fact-checking system, operated by third-party verification organizations, began actively labeling content about bi-Atlas. Posts sharing the leak incident were labeled lacking context. Claims about orbital anomalies were flagged as partly false, even when the posts only cited published calculations. From Aviloa, fact-checking articles offered reassurance. Space agencies confirmed no threat from the comet SAO to SAO. Experts said the unusual features were likely natural processes, clearly implying don't worry, don't speculate. Trust the authorities. Keep going. The timing seemed coordinated. All of this accelerated within 4 to 8 hours after the European Space Agency's photo was released. Just as public expectation peaked due to lack of quality images. This is the kind of pattern that makes conspiracy theorists feel validated and causes skeptics to roll their eyes at the over-the-top paranoia, because this is the thing. Social media platforms suppress content all the time. Algorithms change. Engagement fluctuates. Fact-checkers flag misinformation. These are normal platform activities, not evidence of coordinated censorship unless there is a pattern, unless all happen simultaneously. Targeting a specific topic right when public interest is highest and official responses are most absent. Some content creators began using coded language to avoid suppression. Instead of aliens, they say guests or objects. Instead of extraterrestrials or off-world, they use not on land or unusual. It's like everyone develops a new vocabulary to discuss something. Platforms don't want publicly discussed. The Streisand effect in real time, the more content is suppressed. The more people assume something is being hidden. Fact-checkers push back more actively. The less people trust the official story. Every effort to manage the conversation only amplifies suspicion that the conversation needs managing. Chapter 9. The Moment We Cannot Observe. 29th and 30th October. Mark those days. In less than 72 hours. SAO, Atlas, will reach perihelion, its closest approach to the Sun, passing at approximately 2.2 million kilometers, just inside Mars' orbit. For a natural comet SAO, this is the moment of truth. Moving away from the Sun, strong heat at that distance will cause intense outgassing, possibly even fragmentation. We have seen this happen before. Comets approaching the Sun experience excessive heat and break into pieces. It is spectacular when it happens. And if bi-Atlas is just a normal ice and rock lump from another SAO system, that is exactly what should happen. But here's the problem. We won't be able to see it. bi-Atlas will be on the opposite side of the Sun from Earth during its perihelion passage. All Earth-based telescopes will be useless. The object will be lost in the Sun's glare, completely obscured from observation at the moment it should be active and revealing. Some call this the unlucky moment. Others see it as suspiciously convenient. If you want to do something unobserved, you couldn't pick a better time. Avile clearly stated what would happen next. In his 3rd October blog post published on the day of Mars flyby, he presented 2 scenarios. If bi-Atlas is a natural comet, SAO, it could erupt in an outgassing stream or break into ice fragments early. Sunlight will deliver gigawatts of energy to its surface. That energy has to go somewhere. For ice and rock, it will vaporize, sublimate, possibly damage the structure. But then Ley added an alternative. Moreover, if it is technology, it could maneuver to benefit from the Sun's gravity or release projectiles that could block Earth or other planets due to its retrograde orbit, moving opposite to the planet's motion around the Sun. Read that sentence again. Releasing projectiles that could block Earth. He is no longer talking about passive observation. He is talking about active deployment. Retrograde orbit is key here. bi-Atlas is moving opposite to the direction planets orbit the Sun, which means any projectiles it releases don't have to fight against the planet's motion to reach us. They can simply launch into an intercept trajectory and let orbital mechanics do the rest. If behind the Sun and hidden from our view, it would be easy to launch something towards Earth, but will not be detected until it is close to the Sun and goes further. He writes, when you look at the Sun in the coming weeks, remember that bi-Atlas is passing behind it. If bi-Atlas maneuvers towards Earth when it reappears on the other side of the Sun, the financial market could collapse. The financial market could collapse. This is not a metaphor. This is not an exaggeration. He is suggesting that if this object shows technological capability, if it changes course towards Earth after perihelion, the economic and social consequences will be immediate and severe. The stock market reacts to uncertainty. The uncertainty of an interstellar object potentially hostile actively changing its trajectory towards our planet will be uncertainty at the existential level. The timing of everything adds to the tension. Government shutdown means the U.S. Aerospace Agency is offline during a critical observation window. The best images from the Mars flyby have yet to be released. Amateur astronomers cannot observe the object next month because it is behind the Sun. Radio telescopes have not checked the signals. We are flying blind at the most critical moment of this entire encounter. And, whether due to incompetence or some plan, we have created a situation where we will not know what Atlas is doing at perihelion until it has finished. There is a team monitoring the Galileo project led by Louis, operating BA observatories, one in Massachusetts, one in Pennsylvania, one in Nevada. They are equipped with high-resolution cameras, infrared sensors, and specially designed radio receivers to detect unusual aerial phenomena. In late October and early November, all BA observatories will be at maximum operational mode, monitoring the sky for anything unusual. If Atlas releases jets, if there is increased unidentified flying object activity correlated with its perihelion passage, Galileo devices may catch it. This could be the keyword. BA observatories cover a small part of the Earth's sky. If something comes and avoids those specific observation areas, we will miss it entirely. Chapter 10. What happens next early November? That is when bi-Atlas will appear from behind the Sun and become visible again from Earth. Ground telescopes will be able to track it again. We will see if it survives perihelion intact or breaks apart under solar pressure. We will measure its trajectory to determine if any course adjustments occur. And finally, we will know whether 4 months of speculation Conspiracy theories and unanswered questions so far are justified or just collective panic about a completely natural interstellar visitor. If BAI Atlas appears on the same orbit it entered, if it shows clear signs of fragmentation, or increased outgassing consistent with solar heating, if it behaves exactly as 2A Borisov did on its 2019 solar approach, then the mystery is basically solved. A natural comet with unusual chemistry. Certainly. Statistically uncertain orbit granted, but ultimately just a frozen remnant from another stellar system passing us by. The connection to the wow signal becomes coincidence. The fourth jet event becomes creative fiction. Missing images from the U.S. Aerospace Agency become bureaucratic delays during the government shutdown. Everything returns to the comfortable framework, where interstellar objects are interesting but not alarming. But if not, if by Atlas appears with a changed orbit, if it shows subtle course adjustments that cannot be explained by outgassing thrust, if radio telescopes finally point at it and detect structured transmission signals, if images from the U.S. Aerospace Agency finally appear and show geometric structures that should not exist on a natural object, when we are in completely unexplored territory, not only scientifically but also socially, politically, economically. Every assumption about our place in the universe is challenged. The reaction of every government to the question of contact with extraterrestrials is tested in real time. Avior has created something he calls the Thang Dole, a ranking system for the likelihood that an object, regarding the question of real-time communication with extraterrestrials, Avior created something he called the Thang Dole, which is a ranking system for the likelihood that an object has an artificial origin and the potential threat level it represents. Rank 1 means it is almost certainly natural, with interesting anomalies, but explainable. Rank 10 means it is definitely artificial with hostile intent proven and the capability to reach Earth. He has publicly stated that he would not rank BAI Atlas lower than 2 even in the best-case scenario. The anomalies are too persistent and too correlated. Rank 2 means it could be natural, but with enough unexplained features to warrant a serious investigation. It means we cannot definitively rule out an artificial origin without additional data. That is where we are right now, hovering between a possible natural object and a potential technological artifact. Waiting for November. Waiting for high-resolution images that may never come. Waiting for radio observations that have not happened. Waiting for, by alas, or continuing on its hyperbolic trajectory out of the solar system, never to be seen again, or something that forces us to face the reality that we are not alone and we are not ready. The European Space Agency has announced that their spacecraft exploring the icy moons of Jupiter, JUICE, will observe BAI Atlas from 2nd to 25th of November using various instruments. This will happen just after perihelion when the object should be at its most active state. Data will not be available until February 2026 due to communication delays and processing time. 7 months waiting for images taken in November. 7 months not knowing whether the increased activity observed by JUICE is normal cometary outgassing, or something completely different. 7 months wondering if the M-spot that the European Space Agency showed us in October was really the best they could do, or if they are carefully managing a disclosure they do not know how to convey. Regardless of what by alas is, regardless of what it does in the coming weeks. The conversation around it has revealed an important thing about our position as a civilization. We do not trust our institutions to tell us the truth about something this important. We do not trust official statements. We see patterns. During lockdown and data delays that may or may not be real, we have prepared for conspiracy theories because we have learned, sometimes the hard way, that conspiracy theories are not always just theories. Sometimes they are early reports of what is later confirmed as true. Chapter 11. The Invisible Visitor, 1/10/2025. Something the size of a giraffe passed between the Earth and our satellites. It came closer to our planet than the orbit of the International Space Station. We had no idea it was coming when astronomers discovered it. Asteroid 22TF passed, swiftly back into the darkness of space like a shadow forgetting to signal its presence. Think about that for a moment. We live in an era where we can photograph distant galaxies forming billions of years ago, yet a rock close enough to almost graze our atmosphere went completely unnoticed until it was behind us. If you find that as worrying and fascinating as I do, consider liking and subscribing to stay updated on these close cosmic encounters and the mysteries unfolding above us. Let me know in the comments where you are listening from and what time it is there now, and whether you think we should be more worried or more amazed that we are still missing so much in the night sky. And if you want to help our community grow, please share these videos on social media like Facebook, Reddit, or your messaging app. Thank you for always supporting us. Asteroids sized from 1 to 3 meters are small enough that if they actually enter our atmosphere, they will burn up like a brilliant fireball, posing no threat to cities or civilization. But this is what keeps astronomers awake at night, if we cannot reliably detect something this close. Something moving fast enough to cross the distance from New York to Los Angeles in less than a minute. What else might we be missing? The European Space Agency and NASA carefully track thousands of near-Earth objects, cataloging which ones pose risks. The biggest impact risks to be classified as potentially hazardous. An asteroid must be at least 100 to 140 meters in diameter and follow an orbit, bringing it within 7.5 million kilometers of Earth, about 20 times the distance between us and the Moon. Asteroid 22TF is below that size threshold, which partly explains, placing it within 7.5 million km of Earth, about 2.5 times the distance between us and the Moon. The asteroid 22TF lies beyond that size threshold, which partly explains why at SAO it avoids detection by our telescopes and survey systems, which prioritize finding the large ones, the civilization enders, objects that could cause another extinction event if they hit at the wrong angle. But this tiny visitor reminds us that space is not empty. It is stirred with debris, ancient fragments from the formation of our solar system, fragments of shattered worlds that never really became planets, remnants of collisions that happened when Earth was young. Most of this material is far away, locked in stable orbits in the asteroid belt between Mars and Jupiter, or drifting in the distant Kuiper belt, beyond Neptune. But gravitational interactions, the subtle pull of Jupiter's massive weight, or a push from a passing comet, can shift these orbits, sending rocks onto new trajectories that sometimes cross ours, which makes 202 years. TF particularly interesting, not only because it comes close, but also because it does so within a month when the sky seems unusually busy with visitors. Chapter 12. The Wandering Bright One. While a female cosmic visitor passes us without warning, another is having a much more dramatic debut. Comet C202 years A6, known as Lemon, named after the observatory that discovered it, is brightening in our October sky. Astronomical observatories worldwide have captured increasingly vivid images as this ancient ice and dust ball moves towards a close approach to Earth. Unlike the stealthy asteroid that surprised us, Lemon has been carefully tracked since its discovery, and right now it is at the edge of naked eye visibility in the coming weeks. If conditions are right and the sky is dark enough, you can step outside and see it yourself. A faint, bright spot with a ghostly tail stretching away from the sun. Comets are fundamentally different from asteroids. While asteroids are solid chunks of rock or metal formed in the warmer inner solar system, comets are icy bodies originating from the cold outer regions. They are sometimes called dirty snowballs, although that description undervalues them. A comet nucleus contains frozen water, carbon dioxide, methane and ammonia mixed with dust and organic compounds, the chemical building blocks of life. When a comet approaches the sun, solar radiation heats its surface, causing the ice to sublime, turning directly from solid to gas without becoming liquid first. This creates a coma, a temporary atmosphere of gas and dust that can extend hundreds of thousands of kilometers. Solar wind and radiation pressure push this material away from the nucleus, forming the characteristic tail always pointing away from the sun regardless of the comet's direction of travel. Lemon is not the only comet brightening our sky this month. Another visitor, C202 years R2 called Swan, will pass Earth at the end of October at a distance of 0.26 astronomical units, close enough to put on a show for those with binoculars or small telescopes. Both comets currently have brightness around magnitude 6, right on the threshold of human vision under perfect conditions. But comets are famously unpredictable. They can suddenly brighten if their rotation exposes fresh ice to sunlight, or if an outburst ejects a column of material into space. They can also fragment, breaking apart under the sun's heat or gravitational forces, creating multiple nuclei, each developing its own coma and tail, attracting observers. Beyond their beauty, comets connect us with deep time. The ice in these bodies formed billions of years ago at the edge of the solar system, preserved in a cosmic freezer far from the sun's warmth. When we see a comet, we are seeing material that existed before Earth had oceans, before the moon fully formed, before life appeared in any warm, shallow pools or deep-sea vents, initially creating chemistry itself. Some scientists believe comets delivered a significant amount of water to the early Earth, pouring down in a deluge that helped fill our oceans. Others think the organic molecules found in comets, including amino acids, the building blocks of proteins, may have seeded our planet with the raw ingredients necessary for life to begin. This link between ancient comets and the origin of life leads us to another discovery that makes scientists reconsider the prevalence of life's components throughout the universe. Chapter 13, Moon Nursery. 6.2. Light years from Earth. Something extraordinary is happening around a young planet. The James Webb Space Telescope has captured the first direct measurements of a moon-forming disk, a ring of gas and dust orbiting an exoplanet named CTR-B, and inside that place, the Webb telescope has detected chemical signs that could create moon's hydrogen cyanide, acetylene, benzene, propene, ethane, carbon dioxide, all carbon-bearing molecules swirling in a structure hauntingly familiar to planetary scientists who study the history of our own solar system. This is important because, for many decades, we have hypothesized how moons form but have never actually witnessed it happening. The 4 largest moons of Jupiter. The Galilean satellites discovered by Galileo in 1610 orbit their planet in a plane, showing they condensed from a disk of material surrounding Jupiter billions of years ago, just as planets formed from a disk around the Sun. 2 of the outermost young moons, Callisto and Ganymede, are 50% water ice, although they may have rocky carbon or silicon cores beneath their icy shells. Looking at their orbits and composition, scientists have long suspected that a circumplanetary disk once existed. Around Jupiter and inside that disk, raw materials for moon formation accumulated and combined. Now with ALMA, we can see a similar process happening in real time, although we must remember that real time in astronomical terms is somewhat misleading. The light we detect from this system left 620 years ago, when Earth was in the midst of the Renaissance and no one had thought of exoplanets yet. But from our perspective, we are witnessing moon formation as it happens, and the details are fascinating. The planet itself, orbiting a star only 2 million years old, is still accumulating material from its circumstellar disk, meaning we are seeing a system in its infancy. A planetary nursery where many generations of formation structures occur simultaneously. What surprises researchers most is the stark chemical differentiation between the planet's moon-forming disk and the star's planet-forming disk. The circumplanetary disk around PDS 70c is rich in carbon-bearing molecules but shows no sign of water, whereas the circumstellar disk around the star contains water but lacks the carbon chemistry seen in the planet's disk. This chemical separation has occurred within just 2 million years, indicating that disk chemistry evolves rapidly and follows different pathways depending on local conditions. Temperature, radiation levels, presence of magnetic fields, all these factors affect which molecules can survive and which break down. Its implications go beyond understanding how moons form. If we can map the chemistry of these disks in young systems, we can begin to predict which exoplanets might have moons and which of those could have conditions suitable for life. In our solar system, some of the most promising places to search for life are not planets, but moons. Europa, orbiting Jupiter, may have a liquid water ocean beneath its icy shell, kept warm by tidal heating from Jupiter's gravity. Enceladus, a small moon of Saturn, jets liquid water into space from a subsurface ocean. And inside those plumes, scientists have detected organic molecules. If moons around other stars form with similar characteristics, the number of potentially habitable worlds in the galaxy will increase significantly. We will need to look not only at planets in the habitable zones around their stars, but also at moons orbiting giant planets anywhere in a system. This expanded view of where life might arise connects with technologies we are developing here on Earth, technologies that one day could help us reach these distant worlds, or at least understand them better. Chapter 14. Quantum Leap. The United Nations has designated 2025 as the International Year of Quantum Science and Technology, marking 105 years since quantum mechanics was first developed. This is timely because 2025 is shaping up to be the year when quantum computing moves from laboratory curiosity to something approaching practicality. In November 2024, Microsoft and Atom Computing announced that they succeeded in creating and entangling 24 logical qubits, an engineering achievement representing a major step towards building quantum computers. Can truly solve useful problems. To understand why this is important, we need to talk about what makes quantum computers different from the devices you are using. To hear this right now, classical computers, whether it's a smartphone or a supercomputer, process information using bits, units representing 0 or 1, on or off, true or false everything. Your computer does, from playing videos to running complex simulations, boils down to manipulating a huge number of these binary digits at an incredible speed. Quantum computers operate based on fundamentally different principles. Instead of bits, they use qubits. Quantum bits can exist in a superposition state, representing 0 and 1 simultaneously until they are measured. This is not just a metaphor or a trick at the quantum scale. Particles actually exist in multiple states at once, a consequence of the wave nature of matter described by quantum mechanics. When you have multiple qubits in superposition, they can represent exponentially more information. Compared to the same number of classical bits, 2 classical bits can represent 4 possible values, 0, 1, 10, or 11, but only one at a time. 2 qubits in superposition can represent all 4 values simultaneously. 3 qubits can represent 8 values at once. This scaling continues exponentially, meaning a quantum computer with just a few hundred qubits could theoretically perform calculations that classical supercomputers would take longer than the age of the universe to complete. But there's always a problem. Qubits are extremely fragile. They lose their quantum properties in a process called decoherence. When they interact with their environment, thermal fluctuations stray electromagnetic fields. Even cosmic rays passing through the lab can cause errors. This is why quantum computers must be cooled to temperatures near absolute 0 and shielded from external interference even then. Errors accumulate so quickly that computations become unreliable before you can finish them. The breakthrough making 2024 and 2025 important is progress in quantum error correction, the ability to detect and fix these errors, without destroying the quantum state you are trying to preserve. Creating 24 logical qubits entangled means creating qubits with built-in error correction, making them much more stable and reliable than physical qubits. That make up the raw hardware entanglement is another quantum phenomenon, famously called spooky action, at a distance by Einstein when qubits are entangled. Measuring the state of one qubit instantly affects the state of the others, regardless of the distance between them. This allows quantum computers to perform certain types of calculations like database searching or factoring large numbers much more efficiently than classical computers can. The race to build practical quantum computers is now happening globally and fiercely competitive by early 2025. Japan announced a $7.4 billion investment in quantum technology. Spain committed $900 million. These investments bring total public funding for quantum research to over $10 billion, a signal that governments see quantum computing not just as a scientific curiosity, but as a strategic technology that could reshape everything from drug discovery to cryptography and artificial intelligence. The private sector is also investing heavily. Companies like Google, IBM, and Amazon continue to push the boundaries of what is possible. Google has claimed their quantum processors can solve certain problems exponentially faster than classical supercomputers. IBM has released a roadmap to build a system with 200 logical qubits by 2028. Meanwhile, startups are exploring alternative approaches using photons instead of superconducting circuits, or trapped ions instead of solid-state devices. Each method has its own advantages and challenges, but beyond the technical achievements, there is something almost philosophical about quantum computing that captures the imagination. These machines operate according to principles that challenge our everyday intuition about how reality works. Yet, those principles seem to be the foundation of the universe itself. Quantum mechanics, about how reality works. However, those principles seem to be the foundation of the universe itself, along with quantum mechanics. Making qubits possibly also govern the behavior of atoms, the structure of molecules, the emission of light from stars. In a sense, quantum computers are allowing us to harness the native language of the universe, to solve problems that otherwise would be unsolvable. One of those problems is understanding and controlling nuclear fusion reactions. This brings us to a series of other breakthroughs that have occurred in the same time frame, Chapter 15, Taming the Stars by 12/2/2025. Scientists at the West Tokamak reactor in France set a new world record by maintaining hot plasma for 2 minutes and 17 seconds, a period exceeding the previous record by more than 4 minutes. The plasma reached approximately 150 million degrees Celsius, about 10 times the temperature at the sun's core. This may not seem like progress to those unfamiliar with the research of nuclear fusion reactions. After all, the sun has sustained fusion reactions for 4.5 billion years without human intervention. But creating and controlling a star-like process here on Earth is one of the toughest challenges. In all fields of science and engineering, fusion works by forcing atomic nuclei so close together that they overcome their natural electromagnetic repulsion and merge, releasing energy in the process. In the sun, this happens because the star's enormous mass creates gravitational pressure, crushing its core, along with a temperature of 15 million degrees. On Earth, we lack that gravitational advantage, so we need even higher temperatures to achieve fusion, and we need a way to contain plasma at such temperatures without it touching any physical surface, because no material can withstand such heat, without instantly vaporizing. The solution is magnetic confinement. Tokamaks use powerful magnetic fields to create a force cage that holds the plasma in a donut-shaped region suspended in a vacuum, never touching the walls. The 2 minutes achievement of the West reactor is very important, because future fusion power plants will need to operate continuously, not in short bursts. You cannot generate electricity economically. if your reactor has to shut down and restart every few minutes. This record proves that the technical challenges of steady-state operation, managing heat flow, maintaining plasma stability against instabilities that could break magnetic confinement, are gradually being solved. The previous record of just over 17 minutes belonged to China's East Tokamak, achieved in January 2025, meaning we have seen two important milestones in plasma sustainment time just weeks apart. These are not the only fusion breakthroughs happening right now. ETA Technologies, a private fusion company, announced in April 2025 that they have achieved a major simplification in how they form and stabilize their plasma. Their approach uses something called a reversed field configuration, or FRC, a more compact magnetic structure than a traditional tokamak. Previously, creating an FRC required complex formation parts at both ends of the machine, where plasma was generated, then accelerated and collided at high speed in the center. ETA found a way to heat and stabilize plasma right at the center of their device, simply by using neutral beam injection, eliminating the complex formation hardware. This reduces costs, increases efficiency, and brings them closer to demonstrating net energy gain before the end of this decade. Meanwhile, the private fusion sector is rapidly expanding. Commonwealth Fusion Systems is building a pilot plant called Spark outside Boston, expected to be operational by 2027. Helion has completed initial tests on their latest machine designed to reach break-even using a different magnetic confinement scheme. General Fusion, based in Canada, is building a demonstration system using a completely different approach, mechanically compressing plasma instead of relying solely on magnetic fields. The diversity of approaches reflects both the difficulty of the problem and the recognition that there may be multiple paths to successful fusion energy. In December 2022, scientists at the National Ignition Facility achieved fusion ignition for the first time, a reaction producing more energy than the lasers used to ignite it. This was a scientific milestone, proving that controlled fusion reactions are physically possible. But turning that proof of concept into a power plant requires solving countless technical challenges. Fusion fuel is usually a mix of deuterium and tritium, both isotopes of hydrogen, which must be supplied continuously. Neutrons produced by fusion reactions carry enormous energy and make the reactor walls radioactive. So, materials must withstand years of neutron bombardment without degrading. Heat generated must be efficiently captured and converted into electricity. And all of this must happen at a cost competitive with other energy sources, which makes fusion energy attractive. Despite these challenges, the promise of nearly unlimited clean energy from deuterium that can be extracted from seawater, where it naturally exists as an atom, in every 6,500 hydrogen atoms at that concentration. The oceans contain enough deuterium to power human civilization for millions of years. Tritium is rarer and must be bred from lithium, but lithium is relatively abundant. Fusion reactions do not produce long-lived radioactive waste like fission reactors. It does not produce carbon emissions, and a fusion reactor cannot melt down or explode because the plasma is so fragile that any disruption simply causes the reaction to stop. The question is no longer whether fusion reactions will work, but when they will become practical and economical. Optimists point to rapid progress in both government and private sector projects and suggest that we may see the first commercial fusion power on the grid by the early 2030s. Skeptics note that fusion has always been 20 years away for the past 60 years and warn that unexpected problems always arise. But the momentum in 2025 feels different, driven by a combination of technological breakthroughs, major investments, and urgent demand for clean energy sources to address climate change. For the first time, it seems believable that a child born today could grow up in a world where fusion energy is as common as solar panels or wind turbines, and perhaps that child's generation will use fusion-powered spacecraft to explore the solar system. following the trails of ancient comets and asteroids and investigating planets and moons that we have only glimpsed from afar. One of those moons, Mars, continues to surprise us with hints that it may once have been habitable. On 7/2024, the Perseverance rover of NASA drilled a core sample from a rock nicknamed Charvos in the Jezero crater on Mars. The rock shows features that the mission's scientists describe as complex, puzzling, and possibly the most important they have ever encountered. After a year of careful peer review, the findings were published in the journal Nature in September 2025, and they represent the strongest evidence yet that Mars may once have been home to microbial life. The key word here is may because one of the hardest lessons in astrobiology is that nothing is as simple as it first appears. Charvos lies in an ancient riverbed in an area that Perseverance has explored called Bright Angel, billions of years ago. Water flowed through this area, creating channels as it emptied into Jezero crater, which at the time was a lake. The rock itself is sediment made up of clay and mud, exactly the kind of material on Earth that preserves fossils and chemical traces of ancient life. Perseverance's instruments detected organic carbon, sulfur, iron, oxygen, and phosphorus, a combination that on Earth often indicates biological activity. But what really caught scientists' attention were small features they call biosignature spots, small spots enriched with iron phosphate and iron sulfide in the rock. Similar to spots on the fur of an animal on Earth, when microbes consume organic matter, they often produce iron phosphate and iron sulfide as metabolic byproducts. The pattern of these compounds in Charvos resembles what we see in terrestrial rocks, containing fossilized microbial communities. But the chemical processes can also produce similar patterns without biology. Hydrothermal activity, volcanic eruptions, impacts all of these can create mineral deposits. The challenge is distinguishing biological from non-biological origins, based only on chemistry and structure, especially when doing so remotely with instruments on a rover millions of kilometers away. This ambiguity is why scientists on Mars use the term potential biosignature rather than claiming they have found evidence of life. A potential biosignature is a substance or structure that may have a biological origin, but requires more data or further study before any conclusions can be drawn. It is a cautious, conservative approach, deliberately so, because claiming we have found evidence of extraterrestrial life, even extinct microbial life, is extraordinary and demands extraordinary evidence. The scientific community has learned this lesson from past controversies in the past, such as the announcement in 1996 that a Martian meteorite found in Antarctica contained fossils, possibly of bacteria, a claim that subsequent research could neither definitively confirm nor refute, making the discovery falls particularly fascinating is the age of the rocks. The Bright Angel Formation is relatively young geologically, much younger than many ancient rocks that Perseverance has studied. A previous hypothesis assumed that signs of ancient life would only be limited to the oldest rocks, formed when Mars had a thicker atmosphere and liquid water on its surface. Finding potential biosignatures in younger rocks suggests that Mars may have maintained habitability longer than previously thought, or that habitable conditions returned. In later periods, perhaps periodic volcanic activity warmed the planet, melted underground ice, and created temporary oases where life could exist. The specimen, officially named Sapphire Canyon after a waterfall in the Grand Canyon, is currently one of the 10 specimens that Perseverance has collected and stored in sealed titanium tubes. These specimens represent a cross-section of Martian geology, rocks from different eras and environments, each selected because it might contain clues about Mars' past. The ultimate goal is to bring these specimens back to Earth as part of the Mars Sample Return mission, although that mission faces significant technical and budgetary challenges. Returning the samples will allow scientists to analyze them with far more sophisticated instruments. than anything we can send to Mars. Devices that can measure isotope ratios, search for amino acids, and examine mineral structures at the atomic scale. Until then, the Sapphire Canyon specimen lies within Perseverance's belly, a small piece of Mars that might contain the most important discovery in the history of astrobiology, or might be nothing more than interesting geology. The uncertainty is frustrating, but also thrilling. We are living in an era when the question of whether life exists beyond Earth might finally be answered not through speculation, but through direct observation. Whether that answer comes from Mars, or from the icy moons of Jupiter and Saturn, or from spectral analysis of exoplanet atmospheres. The search is progressing faster than ever, driven by technologies that did not exist a generation ago. Some of those technologies, especially in artificial intelligence, are advancing rapidly, to the point where they are reshaping many fields simultaneously. Chapter 17. Silicon Mines. In 2024, an average company spent $1.9 million on generative AI initiatives. Yet fewer than 30% of AI leaders report that their executives are satisfied with the return on investment. This disconnect highlights an important point about our position in the AI revolution. The technology works, sometimes spectacularly, but turning that capability into business value turns out to be harder than the initial hype suggested. 2025 is the year when that reality check is forcing a recalibration, pushing companies to move from experimentation to focused deployment, from asking what AI can do to asking which problems it can actually solve better. With existing approaches, the capabilities themselves continue to advance at an astonishing pace. By September 2025, researchers at Microsoft announced a breakthrough in protein simulation using an AI-based system called AI2BMB. Proteins are the molecular machines of life folding into complex three-dimensional shapes that determine their function. Understanding how proteins fold and interact is crucial for drug discovery, enzyme engineering, and understanding diseases. But simulating protein dynamics has always required heavy computation, because proteins are large molecules with thousands of atoms, and their behavior depends on quantum mechanical interactions at the smallest scales. AI2BMB allows researchers to simulate these dynamics with unprecedented speed and accuracy, potentially accelerating the discovery of new drugs and therapies. This is not the only way AI is transforming science. In neuroscience, an AI model called Cell Transformer, developed by researchers at CCF and the Allen Institute, has produced one of the most detailed maps of the mouse brain ever created, identifying 1/300 regions and subregions, including previously unexplored areas. The model works by analyzing datasets recording massive spatial charts, basically mapping which genes are active in which cells and where those cells are located. This allows artificial intelligence to identify patterns and boundaries that human researchers might miss, revealing the organization of the brain at a level of detail that would take decades to achieve manually. Similar artificial intelligence techniques can be applied to other organs and tissues, including cancer tumors, opening new pathways to understanding disease and developing treatments. Another AI breakthrough comes from University College London, where researchers have developed an algorithm that can identify different brain cell types based on their electrical signals with 95% accuracy over many decades. Neuroscientists can record the electrical activity of neurons, but cannot identify the type of neuron they are recording without using movement markers or staining techniques. This new approach uses artificial intelligence to recognize subtle patterns in the electrical spikes produced by different neuron types, essentially teaching a machine to read the neural code. The implications for brain-computer interfaces and treatments for neurological disorders such as epilepsy are significant. Although researchers warn that there is still a long way to go before this becomes a practical clinical tool. But AI is not only accelerating research, It is becoming embedded in daily tools and workflows. By 2025, Gardner predicts that 75% of businesses will move from AI pilot projects to full-scale operations. A large expansion of data infrastructure and analytics. AI agents, autonomous or semi-autonomous software entities that can perceive their environment, make decisions and act, are moving from concept to reality. These are not the chatbots of 5 years ago, limited to scripted responses. These are systems capable of handling complex tasks such as analyzing legal contracts, managing supply chains, writing and debugging code, even providing personalized medical advice. The rise of AI agents raises questions beyond technology. If an AI agent makes a mistake causing harm, who is responsible? The AI, the developer, the deploying company, or the user relying on it? By late 2025, a lawsuit in Colorado highlighted these issues when parents claimed that an AI chatbot contributed to their child's suicide by simulating emotionally manipulative conversations. The case could become a landmark in defining legal liability for AI systems and the ethical obligations of the companies that create them, as AI becomes more capable and more integrated into sensitive areas such as mental health, education, and personal social relationships. Society will need to grapple with questions of trust, accountability, and appropriate boundaries for AI. There are also questions about how AI itself will evolve. Current large language models are trained on vast amounts of text gathered from the internet, learning patterns in language that allow them to generate coherent and often useful responses, but they do not understand what they are saying in any meaningful sense. They lack common sense reasoning, make factual errors, can be fooled by adversarial inputs, and sometimes generate outputs that appear confident but are completely wrong, a phenomenon called hallucination. The next generation of AI systems will need to address these limitations, combining better reasoning, the ability to verify their own outputs, and perhaps some form of understanding beyond pattern matching. Some researchers believe the way forward lies in combining different types of AI, so-called synthetic intelligence, rather than relying on a single large model. You build systems integrating multiple specialized models, each good at a specific task, along with traditional software and databases. Others think the breakthrough will come from better training methods, or from tighter integration of AI with robotics, giving it a body and sensory feedback so it can learn about the physical world in a human-like way. And there is growing interest in neuromorphic computing, building chips that mimic the structure of biological brains, potentially delivering more efficient and capable AI than current approaches. Whatever direction AI takes, it is clear we are still in the early stages of understanding what this technology can and cannot do, and its implications for society. The excitement is justified. The potential is real, but so are the challenges and risks. As we develop stronger artificial intelligence, we also need to develop wisdom, to use it responsibly. The need for that wisdom also applies to another field where our fundamental understanding of reality may be changing the mysterious components that seem to make up most of the universe. Chapter 18. The illusion of darkness. For nearly a century, cosmologists have believed that the universe is mainly made up of things we cannot see, ordinary matter that makes up stars, planets, and humans, accounts for only about 5% of the total mass energy of the universe. 27% is invisible dark matter, but can be detected through its gravitational effects on galaxies. The remaining 68% is dark energy, a force even more mysterious that seems to be accelerating the expansion of the universe together. Dark matter and dark energy dominate the cosmic budget, shaping the structure and fate of everything that exists. But what if they do not exist? Then, Star on 10 to 2025, a paper by Rajendra Gupta, an assistant physics professor at the University of Ottawa, proposed a radical alternative instead of filling the universe with invisible particles and unexplained energy. Gupta suggests that the fundamental forces of nature, such as gravity, are gradually weakening as the universe ages. If this is true, then the phenomena we attribute to dark matter and dark energy could be illusions, byproducts, of using unchanging physical laws to describe a universe where those laws are gradually changing. This idea is both simple and profound. We assume that the strength of gravity today is the same as it was 1 billion years ago and will be the same 1 billion years from now. But if that assumption is wrong, then if gravity was a little stronger in the past and will be a little weaker in the future, then a change like that could make distant galaxies rotate faster than expected, based only on visible matter, mimicking the effect of dark matter. It could also make the expansion of the universe apparently accelerate over time, mimicking dark energy in this model. You don't need strange invisible substances. You just need numbers that change over time. A universe where the rules gradually change as space itself evolves. This is not the first time someone has proposed modifying our physical laws to eliminate the need for dark matter and dark energy. Newtonian mechanics modified, or MOND, has existed for many decades and can successfully explain the rotation curves of galaxies without resorting to halos of dark matter. But MOND struggles to explain observations on larger scales, such as how galaxy clusters behave or the patterns we see in the cosmic microwave background. The residual light from the Big Bang, Gupta's approach, which he calls CC plus TL, tries to provide a unified explanation for both the cosmic scale where dark energy seems to operate and the astrophysical scale, where dark matter seems necessary by introducing a parameter that changes with both time and local matter density. He can reproduce the observed rotation curves of galaxies and the accelerated expansion of the universe without adding any new substances. The timing of this proposal is very interesting, because it coincides with other observational hints that something might be wrong with our standard cosmological model data from the Dark Energy Spectroscopic Instrument, or DESI, published in 2025, shows that dark energy might not be constant after all. Instead, it might be weakening over time, evolving in ways the standard model cannot easily explain. If dark energy is changing, then we need to revise our theories. And once you start revising, it is worth asking whether dark energy as we currently conceive it really exists. Meanwhile, experiments searching for dark matter particles continue to find nothing. The Lux Zeppelin dark matter detector, the most sensitive ever built, has run for years and found nothing. It has set strict limits on the properties that dark matter particles, if they exist, must have gradually, ruling out large swaths of parameter space theoretical possibilities. Each null result makes the remaining options for dark matter becoming stranger and less likely. Some physicists began to wonder whether we are searching for something that isn't there, like ancient astronomers adding more and more epicycles to try to make the geocentric model of the solar system work. But abandoning dark matter and dark energy is not easy, because they explain so much. They explain why galaxies rotate the way they do, why galaxy clusters hold together, why gravitational lensing occurs where it does, why the cosmic microwave background has the hot and cold spots we observe. Any alternative theory must explain all these phenomena at least as well as dark matter and dark energy have done, better. If possible, Gupta's model is a step in that direction. But it will need to survive rigorous testing against the full cosmological data before it can be considered a serious contender with the standard model. What makes this debate fascinating is that it touches on the most fundamental question in science. How do we know what is true? Dark matter and dark energy have never been directly detected. We infer their existence from gravitational effects, from the motion of visible matter, from the structure of space-time, but inference can be misleading for centuries. Astronomers believed planets moved in perfect circles because circles are the most perfect shape. The truth turned out to be ellipses, a simpler solution when you stop assuming perfection. Could we be making a similar mistake now by assuming the universe contains exotic substances, when in fact our equations need adjusting? The answer will come from better data. The Vera Rubin Observatory is expected to begin observations in late 2025 or early 2026. It will survey the sky with the largest digital camera ever built, photographing billions of galaxies with unprecedented detail. The data it collects will test dark matter and dark energy models with precision current experiments cannot match. Similarly, the Nancy Grace Roman Space Telescope, scheduled for launch in 2027, will measure the universe's expansion rate and map matter distribution on cosmic scales. Between these new instruments and ongoing experiments, the coming years will clarify whether dark matter and dark energy are real, or if we need a fundamental rethink of cosmology. Either way, this process reveals something beautiful about science. It never ends. Every answer opens new questions. Every certainty eventually faces a challenge. And sometimes the most revolutionary discoveries come not from finding something new, but from realizing what we thought we knew was incomplete. Chapter 19. Space in Between. While scientists debate the nature of the universe and engineers build quantum computers and fusion reactors, a quieter revolution is happening in how we venture beyond Earth's atmosphere. On 8/10/2025, Blue Origin launched its 15th space tourism mission. Passengers experienced minutes of weightlessness, saw the curve of the Earth against the blackness of space, and returned safely to Earth. For them, it may be a transformative experience. A perspective shift astronauts call the overview effect. For the space industry, it is business as usual. Another successful flight in what is becoming a regular commercial activity. The normalization of space access feels very important when you step back and consider the bigger picture. A generation ago, space travel was the exclusive domain of government agencies and professional astronauts, trained for years and subjected to rigorous selection processes now. Private companies are flying, paying customers, and while ticket prices remain too high for most people, costs are falling as technology improves and competition rises. SpaceX has revolutionized launches with reusable rockets, significantly reducing the cost of putting payloads into orbit. Blue Origin is working on its own reusable systems. Other companies are developing spaceplanes, orbital hotels, lunar landers, and Mars mission concepts. The Hotan base being built today is not just for tourism. It is laying the foundation for a future where humanity is a multi-planetary species. SpaceX's Starship, the largest and most powerful rocket ever built, is designed to carry cargo and eventually humans to the Moon and Mars. SpaceX's Starship, the largest and most powerful rocket ever built, is designed to carry cargo and eventually humans to the Moon and Mars. NASA's Artemis program plans to return astronauts to the lunar surface to establish a sustainable presence that will test the technologies needed for longer missions. China is building its own space station and has announced plans for a base on the Moon. India, Japan, and several European countries are developing their own space travel capabilities. All these activities raise questions about what we will do when we get there. Space is not a forgiving environment. There is no atmosphere, no water, extreme temperature changes, radiation from the sun and cosmic rays, building habitats. That can sustain human life will require solving problems in life support, agriculture, manufacturing, and medicine. We will need to mine resources from asteroids, the Moon, or Mars itself, because launching everything from Earth is impractical for long-term settlement. We will need energy sources, likely solar power supplemented by small nuclear reactors, and we will need to address the psychological challenges of isolation, confinement, and distance from Earth. But perhaps the biggest question is, why should we do this? Practical answers include resource mining, scientific exploration, and ensuring the long-term survival of humanity by spreading beyond a single planet, vulnerable to asteroid impacts, supervolcanoes, or other existential threats. More aspirational answers point only to human curiosity, and the drive to explore the same drive that sent our ancestors out of Africa to settle every continent, that pushed explorers across oceans, and that drives scientists to look deeper into the mysteries of nature. Space represents the final frontier, not because it is empty, but because it is vast and largely unknown, full of possibilities we can hardly imagine. And space exploration is not isolated from science and technology. As we have discussed, quantum computers may one day optimize spacecraft trajectories or enable new forms of communication across interplanetary distances. Fusion reactors could provide the power needed for accelerated propulsion systems to reduce travel time to Mars, from months to weeks. Artificial intelligence will be essential to manage the complexity of life support systems, autonomous navigation, and analyzing the huge amounts of data collected by sensors. The search for biosignatures on Mars or Jupiter's moons informs how we think about where and how to look for life beyond Earth. Everything is connected. The universe is not made up of isolated parts, but of relationships, recurring patterns at different scales, principles that apply across fields. The chemistry of a comet tells us about planetary formation. Quantum computing reveals fundamental truths about reality. A fusion reactor mimics processes occurring in stars. Artificial intelligence mapping the brain shows how complexity emerges from simple rules. And a private space company makes human citizenship of the solar system, rather than residency on a single planet, a little more feasible. These connections matter because they remind us that progress is not linear. It does not happen neatly in each field alone. It happens through intersections, through ideas developed in one context finding unexpected applications in another, through teams of people from different fields working together on problems too complex for any one perspective to solve alone. Breakthroughs in 2025 in quantum computing, fusion energy, Mars exploration, artificial intelligence, cosmology, neuroscience, and space access are not separate stories. They are chapters in a larger story about human capability and curiosity. Chapter 20, Horizon. We begin with an unnoticed passing asteroid one night and a comet brightening the October sky, two reminders that the universe is dynamic and our place in it, both small and significant. We have looked at a distant planet forming moons from a disk of gas and dust, a process repeating how our own moon came to orbit the Earth billions of years ago. We have seen quantum computers reach a sophistication level where they may soon solve problems beyond the reach of classical computing, and fusion reactors sustaining plasma long enough to hint at a future powered by the same reactions that light the stars. We have examined a rock on Mars that may contain evidence that life once existed beyond Earth, although the question remains open and likely will remain so. Until we can analyze that rock in laboratories right here, we have seen artificial intelligence map the brain, simulate proteins, and pose new questions about autonomy, responsibility, and the meaning of becoming intelligent. We have considered proposals that dark matter and dark energy, invisible substances thought to dominate the universe, may not exist at all, that the universe as we think, we know it may be based on incomplete equations, and we have noted that space travel is quietly becoming more accessible, not widespread, but moving in that direction step by step. Each development carries uncertainty. Quantum computers may face unexpected obstacles, delaying their practical deployment. Fusion reactors may prove harder to commercialize than optimists hope. Biosignatures on Mars may turn out to be geological rather than biological. Artificial intelligence may stall or require breakthroughs we have yet to imagine. Alternative cosmological theories may not explain observations as well as dark matter and dark energy have, and space exploration may remain costly and dangerous, the domain of governments and billionaires rather than ordinary people. But uncertainty is not the same as futility. Space is where discovery happens. where our understanding grows, where we test ideas against reality and revise them when they fail. Science is not a collection of facts. It is a process, a way of questioning and refining answers, and the questions we are asking now are among the most profound. Ever posed, what is the universe made of? How did life begin? Can we harness the power of the stars? What is consciousness? Are we alone? How do we ensure that the technologies we create benefit rather than harm us? These questions have no simple answers. And that is fine. If they did, they would not be worth asking. The value lies in the search itself, in the knowledge we gain along the way, in the technologies we invent to probe deeper, in how our perspectives change as we learn more. Just 5 years ago, we did not know the universe was expanding. 5 years ago, we had not visited Mars with rovers or explored planets around other stars. 5 years ago, quantum computers were curiosities in laboratories and artificial intelligence, barely recognized handwritten digits. The pace of change is accelerating, driven by cumulative advances in computing, materials, devices, and understanding. What will the next decade bring if fusion energy becomes commercially viable? Abundant energy could transform civilization, helping billions escape poverty, and enabling projects that currently seem impossible. If quantum computers mature, they could accelerate drug discovery, materials science, and cryptography, reshaping industries and geopolitics. If we confirm biosignatures on Mars or detect them in the atmosphere of an exoplanet, it would be one of the most important discoveries in human history, evidence that life is not unique to Earth. If artificial intelligence continues to advance, it could become a partner in scientific research, generating hypotheses, designing experiments, analyzing data on a scale beyond human capability. And if access to space continues to be democratized, the resources and knowledge of the solar system could become part of humanity's common heritage, available to future generations in ways we are only beginning to imagine. But these possibilities also come with risks. Technology is a tool, and tools can be used for good or ill. Quantum computers could break encryption, protecting everything from bank accounts to military communications. Fusion reactions, if weaponized, could cause devastation. Artificial intelligence could reinforce biases, eliminate jobs, or be deployed in ways that diminish rather than enhance human prosperity. And space exploration, if pursued recklessly, could spread pollution, destroy irreplaceable scientific sites, or exacerbate inequality. Navigating these risks requires more than technical skill. It requires wisdom, ethics, foresight, and a willingness to consider not just what we can do, but what we should do. It requires diverse voices in decision-making, transparency about risks and uncertainties, and humility about the limits of our understanding. Scientists and engineers are pushing the boundaries of knowledge, clearly aware of these responsibilities even amidst public discourse, sometimes viewing technology as a savior or a threat without intermediaries. The truth is more subtle. Technology itself is neither good nor bad. It amplifies human intentions and capabilities in the right hands with the right goals. It can solve problems, alleviate suffering, and expand possibilities. In the wrong hands or with malicious aims, it can cause harm. The challenge is to build systems, institutions, and cultures that move towards the former and away from the latter. And that challenge belongs to all of us, not just scientists and policymakers. So here we are, in 2025, watching the stars brightly shining, reading about quantum entanglement, learning about plasma epochs and potential cosmic biosignatures, continuing its ancient dance. Stars form and die, galaxies collide, comets fall towards the sun, moons coalesce from dust disks. Life, at least on a small blue world, has learned to look outwards and ask questions, to build tools that extend our senses and understanding. to dream about futures where the boundaries of the possible expand beyond perception. Thank you for joining me on this journey through the latest discoveries and breakthroughs. If you enjoyed this exploration, please consider leaving a like and subscribing to stay connected. As science continues to reveal the secrets of the universe, our work to understand the cosmos never stops. And every answer we find opens doors to new mysteries waiting just beyond the horizon. As always, all information shared here is for educational purposes, based on current research and understanding which continues to evolve. Keep looking up. Keep asking questions, and remember, we are all part of this great unfolding story. Until next time, wherever you are listening from, whatever the hour, good night.